Okay, so there's sine, there's cosine. Where does tan come from? Or more specifically, where does tangent come from? Okay, so in order to prove this, you can tell just by the name it's going to have something to do with circles, which is why I asked you to draw a circle just now. We're going to take advantage of one particular property of a circle, but rather than just telling it to you, and it's quite intuitively obvious, but I'm actually going to prove it to you. Partly because it will give me the opportunity to give you a cool history lesson, and partly because it will give me the opportunity to show you a kind of proof you almost never see, which is a proof by contradiction. Okay? We're used to proofs by deduction. Right? Deduction. So a deductive geometry proof is the only kind of proof that you're very familiar with and you've been doing for so many years. Okay? It's simple. You start with a true premise, right? I know that this is true. And then you work logically off that premise, and then you arrive at something else which is true. Premise, conclusion. Everything is true along the way. Okay? A proof by contradiction works slightly differently. Okay? It still goes from a premise to a conclusion. Premise to a conclusion. Kind of, right? Instead of going from a true premise to a conclusion, it goes from a false premise, something which actually is demonstrably untrue, and then it goes logically in the same way that a deductive proof goes to, and instead of arriving at a conclusion, you arrive at, from the name, a contradiction, right? You end up at something which clearly can't be, right? Which means that, well, if I went from here to here by purely logical steps that all should make sense, right? And this can't be true, then the problem must not be the logic in here, the problem must be where I started with, okay? There's a very famous proof, you might even remember it, for why root 2 is irrational. That's basically the only proof by contradiction that you would have, you were supposed to learn in the last 12 years of your schooling. If you don't know what it is, I can rehearse it for you afterwards, okay? But I'm going to show you another cool proof to prove a theorem, namely that if I draw a tangent, right, to a circle, it's going to be perpendicular to the radius at the point of contact, okay? So this is not a difficult thing to look at. Like you see, it even looks perpendicular, okay? How are we going to prove it? If what I want to prove is this, that the tangent to a circle is perpendicular to the radius at the point of contact, okay? Remembering how a proof by contradiction is structured, how do you think I should begin? Yeah, again.
Like, draw something wrong.
Okay, well, I've got my drawing there, right? I want a false premise, which I will then draw out to be untrue. The thing that I'm going to pick out which is wrong is, well, let's just say it's not. Let's assume, here's my premise, okay, so I'm going to need a bit more space here, sorry. Let's assume that, I need some labels here, that this tangent is not perpendicular to its radius, okay? I'm going to go from that as my premise, and then we're going to make maths explode, okay? So, let's have a go at this. We need some labels on this thing, so let's call our tangent PQ, okay? Let's make that point of contact, let's call that A. And so what I'm saying is, okay, PQ is tangent to the circle with center O, and that's just by convention. And where it's tangent to the circle is the point A. So here's my setup. Nothing too unusual so far. PQ is tangent, that's true, to the circle at point A, right? Okay, so what I'm going to do here, and I'll put it in another color, and maybe you want to do this or underline it or highlight or something like that. This is going to be my false premise, okay? I'm going to assume that they aren't perpendicular, okay? That PQ is not perpendicular to OA. You okay with that? Now this is wrong, right? This is wrong. But I'm going to take it as if it is true and then just apply some logic and see what happens, okay? Now, just on the side here, you don't need to draw this, but I just want you to have this in your mind's eye, okay? If I have a line, right, and I've got a another line over here. No, that's a bad example. Let's go the other way. Okay, and that angle in there is not a right angle. It's not a right angle, okay? So, like this assumption, that they're not perpendicular, okay? There should be some other point, let's call that one A, right? There should be some other point on this line such that if I do join it up, I will get a right angle. Does that make sense? Like, if that's not a right angle, then somewhere else there ought to be a right angle. There should be a distinct point where I can make that, okay? So what I'm going to do is I'm going to draw another point in. I'm going to draw it up here. Okay? So I'm going to put a point X on this tangent, PQ, and I'm going to say, well, if that's not a right angle, then there should be some other point. I mean, you could put down here if you like, but it's symmetrical, so it doesn't matter, okay? I'm going to construct a point X. There should be another point X such that the perpendicularity is true, okay? So off of this assumption, I should say, therefore, there exists another point. Right? I'm going to call it X such that it is perpendicular. Okay. Now, you'll notice that in constructing OX, I've got another point here which is going to be useful to me. I've got this point here where OX intersects with the circumference, right? Now, being that I've called this A over here, this is another point in the circumference, so I'll just call it B. Okay. So B is where this perpendicular line intersects with the circumference of my circle. All right, let's keep going. Now, remember what I am suggesting, my assumption is that this is not perpendicular, right? So that means I can say that there is another angle that is, right? So I'm saying, I'm putting it in red because it's not true, right? I'm saying that that angle is 90 degrees, okay? So I can then conclude another thing. Again, logically holding this together. Have a look at this triangle in here, OAX. Look at it really carefully, okay? It's very hard because I'm telling you it's something that it's not, but do your best, okay? Since angle OXA is equal to 90 degrees, I can right away make a statement about all the other angles in the triangle, okay? Example, let's put a triangle over here, okay? If I've got a right angle in one of the corners, okay, pick a size for one of the other angles. Pick any size you like, not a rhetorical question, give me a number. 2, sure. 2 degrees, okay? All right, what's the other angle?
90 minus 2.
90 minus 2, which is 88. Okay, fine. That works. I mean, the scale's not great, but it works. All right, give me another angle. That one in the corner. Give me another one. 45. Okay, sure. Let's call that 45. So what does that make the other angle? 45. Okay, now we could play this game for a long time, right? But the point is that whatever angles you come up with, and that I then infer the other angle, okay? Whatever angles you come up with, they're always going to be less than 90. Always, right? You could pick 89.99999 degrees, right? Which would make the other angle 0.00, I forgot how many nines I said. Very small angle, right? But they'll never be more than 90. Why not? Because think, what's the actual reason? Don't just tell me because it can't.
Angles in a triangle add up to 1.
Good. The angle sum of a triangle is 180 degrees. No more, no less, okay? So therefore, these two angles, and by extension any one of these angles, can't be any bigger than 90 degrees. Does that make sense? Okay. So since this angle is 90 degrees, then I can say, therefore, right, angle OAX, it must be less than 90. You happy with that? There's no way it can be even equal to 90. That's why I don't have the inclusion of the boundary. Okay. All right. So far, so good. So if this is 90 and this is less than 90, right, I've got this angle, angle OAX. It absolutely must be less than angle OXA, right? I guess another way of saying this is, since this is a right angle, if you want to use words for it, the other angle must be acute, right? The only way to have an obtuse angle in there is if you can't have a right angle at the same time, right? So this is a right angle and this is acute. All acute angles are less than right angles. That's by definition. Okay? Now here's a really cool thing that you might notice about triangles, right? if an angle in one side is smaller than another angle, right, then its corresponding sides must also preserve that ratio. Let me write it and then I'll show you, okay? OAX, the side opposite is OX, right? That side there, right? If the angle is smaller, then the side that's opposite it must also be smaller. OXA, so its opposite side is OA. Okay? I can get that from that. And you can draw some triangles to make sense of this, right? Clearly, if an angle is small, right? If an angle is small, like that, that's a small angle there, then the side that's opposite it will also be small. Okay? So, you've got a small angle, smaller angle, and you'll have a smaller side. You okay with me so far? I haven't done anything dramatic. This is all just stuff that triangles do. Okay. Now you can start to see where the contradiction is going to flow out, right? OX. When I constructed it, I noticed that it intersected with the circle OB, right? So that means that OX is really the sum of two small intervals, namely OB and, whoops, BX. Yes? It's got two small parts to it, right? And that's less than OA. Uh-oh. I'm in trouble. I'm in trouble because, but OA and OB, by definition, are equal because they're radii. They're both on the circumference, right? And they both go to the center. So therefore, right, I can subtract OA, right, the radius, from both sides, and I get this. Aha. Now I've arrived at what I was after. This is a contradiction. BX is a length. It's right there. BX is a length. But simply by following the rules of geometry and using them from this assumption, I've found a length that is negative. Okay? This is impossible. Okay? You can go through. I did go through a fair few steps there, right? 1, 2, 3, 4, 5, 6 steps, right? You can go and dissect them as much as you like. There's no problem with the 6 steps, right? There's no logical holes in there. The only place where there can be a hole is what I assumed. Okay? So essentially what I've proved is that there is no other point x outside of this that can satisfy this because you end up with a negative length. Okay? And so that's why OA is the only one that can satisfy it.